Hong-Quan from FPT University, Vietnam. It is my honor to present our research at this year's ICACT conference, titled Multi-View Facial Expression Recognition with AU-Guided Heat Maps. This work was conducted in collaboration with Dr. Hong Van Tan and Professor Tu Min Phuong. The ability to recognize and interpret human facial expressions represents one of the most fundamental aspects of human social interaction and emotional communication. Facial expression recognition, FER, is fundamental to effective computing and human-computer interaction, enabling systems to infer emotional states from facial cues. It takes images or videos as input and subsequently classifies expressions into one of 7 basic and universal emotions: anger, disgust, fear, happiness, neutral, sadness, and surprise. The advancement of deep learning techniques has revolutionized the field of computer vision, and FER has benefited substantially from these developments. Deep learning approaches for facial expression recognition have demonstrated remarkable progress, primarily leveraging convolutional neural networks and their variants to learn hierarchical feature representations directly from raw facial. However, these current deep learning approaches rely solely on raw facial images and standard augmentation but lack explicit incorporation of facial anatomical knowledge. This forces models to discover expression discriminative regions from scratch rather than leveraging established facial behavior research. The key contributions of this work can be summarized as follows. First, we propose MVFR, a unified training paradigm that synthesizes 3 data views: original images, augmented flipped images with random erasing for view consistency, and AU-guided heat maps for attention alignment. Second, we introduce a method for generating AU-guided heat maps from facial landmarks in FACS theory, which serve as a signal to guide the spatial attention mechanisms of deep networks toward expression-based regions. We demonstrate consistent performance improvements over state-of-the-art methods on benchmark dataset RAFDB, with ablation studies confirming the progressive gains from each view component. Recent advances in facial expression recognition, FER, have increasingly incorporated domain-specific knowledge to enhance model performance. This section reviews key developments in multi-view learning approach and facial landmark utilization that form the foundation for our work. Recent studies have increasingly adopted multi-view learning paradigms. In this approach, multiple augmented versions of the same input image obtained through transformations including horizontal flipping, random cropping, affine warping, or color space modifications are treated as distinct yet semantically consistent views. Joint learning across these complementary views enhances model robustness and encourages invariance to nuisance factors. However, conventional multi-view augmentation strategies remain generic in nature, as they can be applied to any image recognition task without exploiting the unique anatomical structure of human faces. In contrast, FER presents a distinctive opportunity to leverage domain-specific priors derived from established psychological and anatomical frameworks. Specifically, action units, AUs, as formally defined by the Facial Action Coding System, FACS, developed by Ekman and Friesen in 1978, describe localized regions of facial muscle activity that exhibit strong correlations with emotional expressions. Prior researches in the field of computer vision, such as Martinez et al. In 2019 and Belharbi et al. In 2024, have also established comprehensive mappings between facial expressions and their corresponding action units. Facial landmark detection, which identifies and localizes predefined key points on human faces, has become instrumental in numerous face analysis applications. In FER, researchers have leveraged facial landmarks as informative structural features to complement raw image data. Young et al. In 2017 pioneered this direction by introducing a dual network CNN architecture that processes both facial images and landmarks through weighted summation. Building on this foundation, Meng et al. In 2022 proposed a dual-branch network combining CNN and graph convolutional networks, GCN. Beyond direct landmark utilization, recent research has explored heat map-based approaches to guide model attention toward expression-relevant facial regions. Notably, in previous work, we addressed the question of how to effectively represent facial landmark data, whether raw coordinate positions or heat map-based representations provide better inputs for neural networks, and how to identify optimal fusion strategies for combining heat map-based features with image-based features. These key developments in multi-view learning approach and facial landmark utilization that form the foundation for this work, where we propose a multi-view framework to improve FER performance. It is named as MVFER. The proposed multi-view method, MVFER, is depicted in Figure 5. MVFER utilizes three complementary views: original facial images and horizontally flipped augmented images as dual input branches, while AU-guided heat maps, derived from facial landmarks and FACS theory, to guide attention toward expression-critical regions including the eyes, brows, and mouth areas. The framework employs a unified training paradigm ensuring consistent representation learning across both input views while aligning learned attention with expression-relevant facial regions. This integration of multi-view learning and attention alignment enables our proposed method, named MVFER, to achieve enhanced facial expression recognition performance. During training, the pair X_1 is fed into a shared backbone network and classifier head to produce class predictions and feature representations, while X_3 is used for attention alignment. During the validation and inference phases, only the original view of each image in the test set is employed. Each image is fed into the trained backbone network to generate class logits, which are subsequently passed through a softmax layer to obtain a probability distribution over the 7 expression categories: surprise, fear, disgust, happiness, sadness, anger, and neutral. The final prediction is determined by selecting the class with the highest probability. As mentioned, instead of using landmark-derived heat maps as direct input features, we generate AU-guided heat maps that serve purely as supervisory signals to guide attention learning, essentially teaching the network where to focus on expression-critical regions. The Facial Action Coding System, FACS, by Ekman in 1978 provides an anatomically grounded framework for decomposing facial expressions into action units, AUs, elementary muscle movements that form the basis of emotional displays. Each basic emotion is characterized by a distinctive subset of AUs localized to specific facial regions, enabling systematic computational analysis of expressions. This established knowledge enables us to construct AU-guided heat maps that direct attention toward expression-relevant areas. Figure 6 illustrates our pipeline of generating AU-guided heat maps. The process initiates with facial landmark detection on the input image, providing precise spatial coordinates for key facial features. These detected landmarks are subsequently mapped to anatomically meaningful facial regions that correspond to expression-critical areas as defined by FACS theory. The systematic construction of expression-specific heat maps is enabled through the integration of expert knowledge via pre-established lookup tables, Tables 1 and 2. These tables provide comprehensive mappings between facial expressions and their corresponding action units, as well as the spatial relationships between AUs and specific facial regions. We evaluate the effectiveness of our proposed method on the Real-World Effective Faces Database, RAFDB, a widely adopted benchmark for facial expression recognition. The dataset has been carefully curated to cover diverse conditions, including variations in age, gender, ethnicity, head pose, illumination, and occlusion, making it highly representative of real-world FER challenges. It is also important to note that the dataset is highly imbalanced, with an imbalance ratio of 16.78, reflecting substantial variation in class frequencies. In our experimental evaluation, we employed ResNet as the backbone network, following established practices in recent facial expression recognition literature to ensure fair comparison with state-of-the-art methods that utilize similar pre-training strategies. At a first glance, Figure 7 depicts the training and validation performance of the proposed model across 100 epochs. The validation curves closely follow the trends observed in the training curves. Leveraging pre-trained weights, the model converges rapidly, with training loss nearing zero by epoch 30. Validation curves stabilize after 20 epochs, but accuracy remains competitive, around 88%, demonstrating effective generalization to unseen data. We benchmark MVFER against state-of-the-art methods on the RAFDB dataset using the evaluation setup described above. MVFER is assessed in 3 variants, demonstrating progressive improvements through the integration of augmented views and AU-guided heat map views. The quantitative results are reported in Table 3. Our full 3-view MVFR framework achieves an accuracy of 89.54%, exceeding the recent strong published works, Guided Interpretable FER, 88.95%, by plus 0.59 percentage points, and EASY, 88.75%, by plus 0.79 percentage points. Because these comparisons use the same ResNet 50 backbone as several competitors, the gains can be attributed to our multi-view learning design rather than architectural capacity. Notably, the 2-view variant, without any landmark information, already attains 88.75%, matching the best landmark-free baseline, EASY, 88.75%. When landmarks are introduced only as structured supervision, not as input features, MVFR rises to 89.54%, outperforming all landmark-based methods, including PZNN, RAN, OADN, FERDN, and Guided Interpretable FER. To demonstrate the effectiveness of each component in our framework, we conducted ablation experiments comparing 3 variants of our approach. 1. Single-view baseline using only original images. 2. 2-view variant incorporating original and augmented images. And 3. The full MVFER framework including AU-guided heat maps. The results reveal substantial progressive improvements. The single-view baseline achieves 85.43% accuracy, while the addition of the augmented view, horizontally flipped images, dramatically improves performance to 88.75%, plus 3.32 percentage points. The incorporation of AU-guided heat maps in the full MVFR framework further enhances accuracy to 89.54%, plus 0.79 percentage points, representing a cumulative improvement of plus 4.11 percentage points over the single-view baseline. Ablation studies reveal that the incorporation of flipped views contributes the majority of the performance improvement, while AU-guided supervision provides consistent additional enhancement. Finally, an examination of the class-wise expression accuracy reveals that the proposed model achieves strong recognition performance for several categories, most notably happiness, 95.27%, neutral, 90.44%, and sadness, 88.08%. In contrast, fear, 60.81%, remains the most challenging category, largely due to its similarity with expressions such as surprise and sadness. This outcome aligns with prior findings in the FER literature, which highlight the inherent difficulty of distinguishing subtle expressions like fear and disgust from neighboring affective states. We introduced MVFER, a novel multi-view facial expression recognition framework that fundamentally differs from existing approaches in its systematic integration of domain-specific knowledge with multi-view learning paradigms. Instead of consuming AU heat maps as inputs, we recast them as structured supervisory signals that align network attention with expression discriminative regions, while a dual-branch architecture processes each image and its horizontal flip to enforce flip semantic consistency. Empirically, MVFR achieves 89.54% accuracy on RAFDB, surpassing recent strong published works that employ the same ResNet backbone, thereby demonstrating that performance gains arise from our multi-view modeling approach rather than architectural advantages. Future work includes the development of self-supervised cross-view alignment mechanisms that could eliminate landmark dependencies while preserving the benefits of structured anatomical guidance.